Here's an example. We're given this circuit, which we recognize as a series circuit. Then we know that the current in every part of this series circuit is the same, so the current in each of these components is going to be the same. Part A says that for each 20 milliseconds, 40 microcoulombs of charge leaves the negative terminal of the battery. What is the current through resistor R1? So we're asked to find the current through R1, which is this current. We can label this current I. Now we know that the current everywhere is the same in the series circuit, so this is also I. And this is the current leaving the negative terminal of the battery. We're told that each 20 milliseconds, 40 microcoulombs of charge leaves that negative terminal, and we want to know the current through R1. So we're given that time t is equal to 20 milliseconds, and that's 20 times 10 to the negative 3 seconds. And we're also told that charge Q is 40 times 10 to the negative 6 coulombs. We're asked to find the current, and again, because it's a series circuit, we know the current will be the same everywhere. Now, what relationship do we know that relates together the known information with the unknown information? Remember that current is defined as charge divided by time, and that's the key to solving the first part of this problem. So the current is charge, that's 40 times 10 to the minus 6 coulombs, divided by time, which is 20 times 10 to the minus 3 seconds. 40 divided by 20 is 2 times 10 to the negative 6 minus negative 3, since we're dividing. That will be negative 6 plus 3, that's negative 3. The result is 2 times 10 to the negative 3 amps, or 2 milliamps. This is the current through the resistor R1, but since this is a series circuit, this is also the current through the entire circuit. For part B, we are asked what is the voltage across the 1.2 k-ohm resistor. Here's the 1.2 k-ohm resistor, and we can label the voltage across it. It's always a good idea to label the variables that you're given and trying to find, so we'll call that value V. In part B, we are given that the resistance R is 1.2 times 10 to the third ohms. Also, we know from our previous result that the current through this resistor, which is the same in the entire series circuit, is 2 times 10 to the negative 3 amps. And what are we asked to find? It is the voltage that we've labeled as V across that 1.2 k-ohm resistor. Now, what information do we know that relates together voltage, resistance, and current? Well, of course, we have Ohm's law. Voltage equals current times resistance. Since we know both current and resistance, we can solve for the voltage. We can write that the voltage V is equal to current 2 times 10 to the negative 3 times resistance 1.2 times 10 to the third ohms. Now, 10 to the negative 3 times 10 to the third is 1, and 2 times 1.2 is 2.4. Dimensionally, an amp times an ohm is a volt. And that's what we were asked to find the voltage across the resistor, which is 2.4 volts. Now for part C, how much power is used by the 2.5 k-ohm load? Here's the 2.5 k-ohm load. What do we know about that resistor? Well, we know the current through it. The current is the same everywhere in this series circuit, so that's 2 times 10 to the negative 3 amps. And the resistance in this case is 2.5 times 10 to the third ohms. We need to find the power, P. So what do we know that relates power, current, and resistance? Well, we recall that power can be written as current squared times resistance, and that relationship will be useful for solving the last part of this problem. Power is current squared, that's 2 times 10 to the negative 3 amps squared, times 2.5 times 10 to the third ohms. Now, 2 times 10 to the minus 3 squared is the same as 2 times 10 to the minus third amps times 2 times 10 to the minus third amps times 2.5 times 2 to the third ohms. 10 to the minus 3 times 10 to the third is 1, leaving 2 times 2.5, that's 5, times 2 is 10, and then times 10 to the negative 3. and that will have units of watts. So, 10 milliwatts is the power dissipated by the 2.5 k ohm resistor.